Hi, and welcome to the third part of this lecture on applications and advances of deep reinforcement learning. As you have seen last week, a model-based reinforcement learning method estimates or knows explicitly the transition dynamics, that is, the probabilities for going from state S to state S prime under action A, and also the reward structure, for example, the rewards that are given when such transition happens. Now, in this section, you will learn how such a model can actually be used for planning. We will then see how we can use standard planning methods in deep reinforcement learning, for example, with variational state tabulation. You will learn that we may prefer decision time planning over background planning in large state spaces. You will then see how AlphaZero, the famous application where an algorithm finally beat the world master in the game of Go, how it learned to play Go and how it uses Monte Carlo tree search. And finally, we will combine what we have seen in the previous subsections of this lecture, and you will learn how mu0 reaches the same level as AlphaZero without even explicitly knowing the rules of any game. To speak about planning methods, I will present to you a very simple deterministic example on the next slide. I won't go into details, but recommend that you have a look at Sutton and Bartos chapter 8 if you want to know a bit more about planning methods. So the simple deterministic example is the following. We have here an extremely simplified version of a map of Europe. We have Rome, Palermo, Bari, Nice, Milan, Vienna, Frankfurt, Zurich, and Lausanne. Now, the dynamics is deterministic. So if you are in Milan and you take action south, you will end with probability 1 in Rome, and what you have to pay, or if you want the reward here, is -6, standing for 600 kilometers that you need to travel from Milan to Rome. Now, having this map, this simplified map of Europe here, we can compute for every city on this map, for every city that we have in this model, what is the action that would lead as quickly as possible to Rome, and how much would be the reward? How many kilometers would one have to pay to reach Rome? A simple method is the following. You start in R, in Rome, and now for every state S that leads to Rome, so that is for every state S that has a non-zero probability to go to Rome by taking some action A, one computes the value of that state by just taking the maximum over all the actions that lead to Rome. In this simple example, it's only one because we have deterministic dynamics. And we would end up, for example, with the value of Milan being -6, the value of Nice -7, value of Palermo -9, value of Bari -4. Now, having computed the values of the neighboring cities of Rome, we can continue, and for every state S that leads to an already visited state S prime, compute its value with the following formula. So the value of a state is the maximum over all the actions, averaging over all the possible next states that we can take in this state and action A, and with probabilities corresponding to the visitation probability of S prime. In this case, again, this is very simple because we're in deterministic dynamics. And we add up just the reward for this action, for this immediate action, plus the value of the next state, of the next city. I did not include a discount factor gamma here because we are in an episodic setting that ends when the agent reaches Rome, but we could include a discount factor gamma. So for example, we can compute the value for Lausanne by looking at the Q value for the action south. So from Lausanne, taking action south would cost -6, or would be reward -6, plus the value of Nice, which is -7. So in total, we end up with -13. Looking at the Q value for action southeast and going to Milan, we realize that it's actually better because we just add up the -3 plus the -6, the value of Milan itself, and reach at -9, which eventually is the value of Lausanne. And by having computed the three different Q values for Lausanne, actually that one for moving straight east or a little bit northeast, for moving to Zurich, the cost would be -11, so the Q value for this action would be -11. And we see now, by having these three Q values for Lausanne and the value of Lausanne, we know which action to take, and also we know if from Zurich we would want to go through Lausanne to Rome, we would know which value we would need to take for Lausanne. Now this this step 3 can now be iterated further to also compute the values. Well, the only value that is left, I guess, in this case is the one for Frankfurt, and we can compute this as we did already for the other states. Now, this simple deterministic example can be generalized to stochastic examples with loops, and the generalization is called value iteration, and it simply works by starting with arbitrary values for all the cities in this graph, for all the states in a certain environment, and then iterate this equation 1 here until it does not change anymore. And this is called value iteration. Now what is important about this method is that it does not at all care about where we even start. I mean, we just, by computing or by running value iteration, we will learn about the values, the V values and the Q values of all the cities in this graph, and afterwards we can just use these Q values, for example, to know that from Frankfurt we should go to Zurich and not to Vienna to go as fast as possible to Rome. Now, if we would switch the goal, if we would instead of, if we wanted to go to Vienna instead of going to Rome, we could just run value iteration again with the new terminal state V, and we don't need to do any experience in this environment. We don't need to travel a little bit. We don't need to travel at all, and we would could compute with value iteration the values and the V values and the Q values of this graph for a new terminal state. And I would want to mention here also that this also works in the infinite horizon setting, where we don't have a terminal state, if we just include the discount factor gamma here in this equation here. So this equation here is very powerful, and iterating it until convergence will always give us the V and actually also the Q values for a certain model. Now this is called background planning because the V values and the Q values here are computed without actually performing any action in the environment. Just by knowing the transition dynamics and knowing the rewards and where the terminal states are, we can compute the V and the Q values in the background. That's why it is called background planning. Now, how can we apply this kind of background planning in a setting where we would use deep reinforcement learning? In a study that was performed by PhD student Dane Cornell in the lab of Wolfram Gerstner, we looked at navigation in this Doom environment. So that's an environment that some of you may know from playing video games. And the task that we set the artificial agent to do was to move around in this maze from arbitrary start locations and find a goal location. Now, where is the model here? How can we do model-based planning or model-based reinforcement learning in this setting, you may wonder? Because planning with this high-dimensional video input may be very difficult. So the key idea of this approach here was to learn to encode images as discrete states such that similar images O are mapped to the same discrete state S. So for example, the current observation may be one that is taken at the start of a hallway. Now, this state being at the beginning of a hallway can correspond to different observations depending on if you turn a little bit to the left or a little bit to the right, or you move a little bit forward or a little bit backward, but still basically being in the state at the beginning of this corridor is one discrete state. And we represent this discrete state. We call it a discrete latent state because it's not directly observed, but this being at the beginning of a corridor can be seen as the actual state that the agent is in. And we encode this state with a binary vector, actually. Now, this binary vector being part of a rather small state space, so we have here 5 bits, so 2 to the 5 different states that the agent actually can be in. And after performing some action, the agent moves to a new state that is again represented by a different binary word. And this binary word would then correspond to the discrete state being somewhere in the middle of this hallway from which we started. Now, if we have this latent representation where the discrete states correspond to more abstract locations in this environment, we can now use standard background planning methods for efficient reinforcement learning. So whenever the agent learns something new about the environment, for example, that taking the action forward at the beginning of this hallway will lead to being somewhere in the middle of the hallway, then the transition probability from, well, this transition probability here changes, or also the reward can change because the agent may encounter dangerous zones or rewards in this environment. And then we can just update offline in the background the policy by running a smart version of value iteration, which is called prioritized sweeping. Just as a little side remark about how we actually learned these discrete latent representations, what we used in this work here was a deconvolutional neural network, that it's like the inverse operation of a convolutional neural network that takes these discrete states as input and produces images as output. And with this, what is called the reconstruction network, with this deconvolutional network, we can then train also a convolutional network that takes observations two latent states, two such binary discrete representations, and basically one can train this convolutional network that maps now observations to discrete latent states through backpropagation by going through the latent state and back through the deconvolutional network to reconstruct images. And like in this way, one can train with backpropagation, with the backpropagation algorithm that you've seen, the convolutional network that is here used to encode the raw observations as discrete latent states. To summarize this part, in model-based reinforcement learning, we can use background planning to update the Q and V values efficiently, for example by value iteration, if the number of states and actions is not too large. Now in the context of deep reinforcement learning, where we have, for example, high-dimensional inputs like images, it may be useful to use learned abstractions that map high-dimensional states like images to discrete states that can then be used with the standard planning methods, the standard tabular planning methods that we know.